equivalent as a function of the percentage of pipelines requiring repairs when exposed to that soil. Again, the higher the percentage of repairs, the greater the corrosion of steel in that environment. And we see as the total acidity increases from 7.5 to 12 to 18 to 22, as the acid becomes more acidic, the percentage requiring repairs increases. So we go from 6 to 13 to 21 to 31%. The general dependency for steel in the soils is that as the acidity increases, the corrosivity increases of the soil. We're talking primarily about steels. Here again, there are some qualitative measurements we can make. A soil with a pH of less than 4.5 would be referred to as extremely acidic. From pH 6 to 7 to 8, we would refer to it as being a neutral soil, and a pH of a soil measurement that had a measurement on the order of 9 or 10 would be referred to as an extremely alkaline soil. So the pH of soils range on the order from about 4 to 10, with the bulk of the soils having essentially neutral type conditions. Bacteria can grow and thrive under many conditions in soils adjacent to the metal pipeline or the metal tank. One of the most common bad actors we find in that grow under anaerobic conditions where we have no oxygen present. And there's a strain of bacteria that are called sulfate reducing bacteria, and part of their metabolism, they convert sulfates in the environment to sulfides. Sulfates are rather innocuous in corrosion reactions. Sulfides can be extremely corrosive. And so what we find is under the conditions where these colonies of bacteria grow, they actually modify the environment and make it much more corrosive. The characteristics we talked about so far have been primarily concerned with corrosion of a single metal, steel or aluminum or whatever in a buried structure. We also have to be concerned about galvanic corrosion in the soils. That is where we hook two dissimilar metals together. And we, in fact, can have a galvanic series for metals in the corrosive environments. And as we have a galvanic series for seawater, we can also develop a galvanic series of typical materials in a neutral soil. And these will range from the more noble materials that will act as a cathode to the more active materials that will act as the anode. And we see here, measuring these with respect to a copper-copper sulfate electrode, graphite is fairly noble at plus 0.3. Zinc is very active at minus 1.1. If we hook zinc to a piece of graphite in the soil, we're going to greatly accelerate the corrosion of the corrosion of the zinc because of its contact with graphite. Mill-scaled steel that contains the black metal oxide from hot rolling on its surface, Fe3O4, has a value of about minus 0.2 with respect to a clean steel surface, which has a potential of about minus 0.7. If we have a bare steel surface in contact with a mill-scaled surface, we'll find that that mill scale can in fact act as an efficient cathode and accelerate the corrosion of clean steel. Rusted steel, steel that's already got a corrosion product on it, is likely to be cathodic to a brand new piece of bare steel connected to it. And so you can see here as we go through, copper alloys are more noble, cast irons somewhere in the center, steel, aluminum, and zinc are more active. We can use zinc to cathodically protect steel under certain conditions in the soil, but we have to make sure that the zinc does not passivate, shift its position. So we can develop essentially a galvanic series for materials in the soils. And that's very useful if we're combining various structures in a steel. A common example of corrosion problems we run into are where brass plumbing and brass valves are connected to a steel pipe and then exposed to a moist environment. How do we control corrosion in soils? Well, we have several characteristics. We can control the corrosion of steel typically by the combined use of protective coatings, organic coatings, paint systems, polymer systems, and back that up with a cathodic protection system. This by far is the best way to control corrosion of steels. The coating covers up the bulk of the surface, and the cathodic protection provides a backup protection at those areas where we have exposed steel. We can go to cast iron. We can go to more corrosion-resistant alloys, copper alloys, much more corrosion-resistant in soils, or we can go to non-metallics. Much greater increase in the use of PVC pipe and other plastic pipe for applications of materials in buried structures. Another important characteristic in soils with cathodic protection, and we'll cover it here and again in a segment on cathodic protection, is the likelihood of stray current corrosion. And this concept is, if we have current passing through the soil, just from spot A to spot B, and we happen to bury a tank or a pipeline in that vicinity, what will happen is the current takes the path of least resistance. So it jumps onto the pipe at this place, or steel structure, moves around because the resistance through the pipe is less than that in the soil, and jumps off at this point. This is good news. That part of the pipe will be cathodically protected where current enters. The bad news is where the stray current jumps off the pipe, and we'll get accelerated corrosion in that area. This can happen again when we have a structure protected and another structure in the vicinity of that. The current can be running down the pipeline. It can jump off at a convenient spot of close proximity to the other pipeline and run down that pipeline and subsequently jump it off someplace else. Again, the stray current causes problems where the current leaves the pipe. That's going to be the anodes. And so if we have electrical currents passing through the earth, we have to be concerned about steel structures, metallic structures, because of this stray current corrosion that can occur. Where can it jump on and where can it jump off? There are several test methods in which we can go out into an actual application and determine, is stray current corrosion a problem, is it occurring, and what's the magnitude of it? And there again, there's technology which will allow us to eliminate or alleviate the stray current corrosion problems.
Soil characteristics important to studying corrosion include electrical resistivity, aeration or permeability, pH, and bacterial presence. Low electrical resistivity in a soil promotes corrosion more than soil with high resistivity. In general, the stronger a soil's acidity, the higher the corrosion rate it produces. Controlling corrosion of steel in soil often involves use of organic coatings or paint, cathodic protection, or switching to alternative materials like cast iron, copper alloys, or plastic pipe. In stray current corrosion, corrosion occurs where current exits the metal pipeline.
Let's shift gears once again and talk about corrosion in various liquids. And the first that we'll talk about is a classification of the various liquid environments. And we'll talk briefly about corrosion in natural waters. We'll talk about corrosion in treated waters, those that we've given an intentional water treatment to. We'll talk about corrosion in acids, and we'll talk about corrosion in alkalis. So first of all, let's discuss corrosion in natural waters. We can talk about fresh waters, such as we find in Lake Erie. We can talk about seawater, such as we find in the various oceans. Brackish water is what we find at the outflows of rivers into seawater. There's the area where we have mixed salinity, mixtures of seawater and fresh water, and we refer to those as brackish waters. Commonly encountered corrosive environments where we have metal structures being exposed to these environments. Geothermal brines are used for power generation and for heating supplies. Again, these can contain high amounts of dissolved solids. They can contain hydrogen sulfide, other corrosive gases, and we can find in some cases much higher brine solutions. We can characterize the corrosion of seawater or marine environments by listing essentially the important properties of seawater with respect to corrosion reactions. So what's important of seawater characteristically from a standpoint of corrosion? Those are listed in the next slide. And what we find is that, first of all, seawater around the world is on the order of about 3.4% sodium chloride solution, salt. It's a highly conductive environment, so it's able to maintain current, conduct current from the anodes and cathodes over long areas. Most of the oceans have a significant amount of oxygen dissolved in them, even to great depths. Velocity is a very important parameter in seawater. Stagnant seawater is considerably different than flowing seawater from a corrosion standpoint. The temperature and the biological activity are yet other important parameters. We can characterize the corrosion that we observe in marine environments, in seawater, based on various zones. And what we're plotting on this diagram is the relative loss in metal thickness, that is, increasing corrosion rate across this axis, as a function of the depth of the seawater. And what we're pointing out are the various zones. What we find is up in the atmospheric zone, at the high parts of the atmospheric zone, we see moderate corrosion rates. They increase as we get down, the time of wetness increases. In the area where we have tide, mean tide going up and down, alternate immersion, we have highly corrosion rates. At the lower end of that, we see this small zone where corrosion, in fact, is fairly low. This is if we buried, the way this data was taken is a piling was buried, so we have a continuous metallic structure. This drop here is due to the differential aeration effect. High oxygen area acts as a cathode and promotes corrosion on either side of it. Individual panels buried here wouldn't show this decrease in the curve. As we get down in a totally immersed area, we find a corrosion rate dropping, and we down in a mud line, it's down even lower. This data was reported in a Metals and Ceramics Institute Center report and for corrosion behavior of metals in seawater. The other aspect of marine corrosion, if we're talking about the corrosion behavior of stainless steel and other materials that depend upon their passive film, chloride ion can be very aggressive. And this is an example of some stainless steel rods. You can see the multiple pits along that rod after it's been exposed to seawater. This is a higher magnification shot. You can see the amount of damage that's incurred here. In fact, we find that in the seawater, stagnant seawater is much more corrosive for the stainless steels and those materials that depend upon passivity than is flowing seawater. And in fact, the common corrosion control technology is for stainless steel piping to maintain the flow of moisture, flow of water through the piping system continually, or else to shut down and to drain the system in times of shutdown. If we allow stagnant seawater to sit in the piping system, then what can happen is solids in the pipe can deposit out on the pipeline, and we get concentration cells started, and we see pits and concentrated severe corrosion underneath those deposits. There's a tremendous wealth of data on corrosion in marine environments because it's such an important environment to us for the shipping, obviously, Navy, and so forth. The next set of discussion will refer to the potable waters, the treated waters, and this can go from the extreme of potable waters, drinking water essentially, that's pumped through our homes and places of work. Demineralized water, which is simply water where the solid constituents, the scale-forming constituents, have been removed or partially removed. Boiler feed water is yet another category of treated waters, and these are waters that are treated to go through power plant boilers and other systems where we're making either processed steam or steam to drive turbines, and we find that we have to treat that water specifically to control corrosion. Processed water would refer to the waters which are used throughout an industrial plant, and cooling waters in the same category, recirculated and pumping systems. The next slide shows an example of something that's had a major impact on the cooling water industry, and that is cooling water towers. There's a tremendous difference in the corrosion control technology that can be used for water treatment when we're passing water through a cooling tower, as shown here, versus a closed system of pipe loops in an actual process. The exposure of the solution to that atmosphere changes the types of inhibitors we can use, it changes the oxygen concentration obviously, and the corrosion control technology has to be significantly changed for systems where cooling towers are being used as opposed to cooling ponds or recirculating water systems. What are some of the factors that affect corrosion in the liquid environments? Let's list those, and what we find in the next slide is the list is similar in many ways to the factors we called out in the beginning. We're interested in the physical configuration. What are the flows through the system? Where is the system wet? Is it wet or dry? How does the system operate? What's the chemistry of the water? And under chemistry, we lump the conductivity, the pH, the oxidizing potential. What are the dissolved species there, chlorides, sulfides, etc. Are solids present in the system? If we have particles sweeping along the system in contact with the piping and the tanks, then we can have some abrasion and mechanical aspects of the corrosion. So the presence or absence of solids is important. What's the flow rate? The higher the velocity, the greater the possibility that we'll get into abrasion type problems. Temperature again, corrosion increases with temperature. And here again, as we found in the soils, biological species can be present that will promote corrosion. We've talked about the top of those characteristics pretty much earlier. Let's focus a little bit more on the biological corrosion. And some of the microorganisms, there are several different families of bacterial or microorganisms that can affect corrosion. Some of the corrosion effect can simply be by forming a product on the surface and causing concentration cell corrosion. And there's a whole family of bacteria that form slimes and other green gooey things on pipes and exposed parts. The bacteria themselves can produce a more corrosive environment. An example of that is the desulfovibrio, bacteria, and these are one of the family of sulfate-reducing bacteria. As part of their metabolism, they actually produce sulfide, which increases the corrosion. Some bacteria deposit iron. They can actually take metal and make that part of their metabolism and form the corrosion right as part of their actual biological function. Algae and fungi serve similarly to these throughout. What we'd like to do now is discuss the corrosion in some of these liquid environments, and we'll talk about corrosion in acids, we'll talk about, and then we'll finish off by talking about corrosion in some alkaline solutions. Let's contrast from the standpoint of pointing out basic concepts of corrosion, the corrosion behavior in hydrochloric, sulfuric, and nitric acids. There are other acids of importance, but we're going to discuss those three in a little bit of detail here. All of these acids are strong acids. They all have very low pHs in even dilute environments, dilute mixtures of them, and yet the materials that we can use in each of those acids are considerably different because of the nature of the environments themselves. Let's contrast those. First, we'll talk about hydrochloric acid. General appearance here of steel, general behavior of steel and hydrochloric acid. What we find is that as the hydrochloric acid concentration increases, the corrosion rate increases. And so we see this general behavior where increasing acid, increasing corrosion rate. Hydrochloric acid is a highly reducing acid. There's no stable film that forms on the acid, and so we see no exhibit of passivation and no retardation of the corrosion rate as the concentration increases. The corrosion rate continues to increase with acid concentration. We don't form any insoluble film, so we don't see any passivity in this particular steel and hydrochloric acid. The use of inhibitors can be very effective in controlling corrosion in hydrochloric acid. Another useful concept that's introduced by Fontana in his book on corrosion engineering is this concept of classes of materials. And he essentially categorizes class 1, 2, and 3 materials. Class 1 being those materials that can be generally used. Class 2, those materials which can be sometimes used, and Class 3, those materials which cannot be used at all. And what we have here is a listing of those materials for metals in hydrochloric acid. So we're taking metals in hydrochloric acid and we list those Class 1 materials. These are the materials that are generally acceptable for hydrochloric acid service over a wide range of compositions. We see that that includes nickel-molybdenum alloys, nickel-moly-chrome alloys, tantalum, zirconium, molybdenum, and high silicon iron with molybdenum added. These are the acceptable classes of metals to handle hydrochloric acid. Class 2 materials are those that can be used under certain conditions. And we can use copper and copper alloys under certain conditions. Those certain conditions are when we have highly reducing hydrochloric acid. That means we have no oxygen present, we don't have any other oxidizing species. If that's the case, copper and copper alloys are quite good. If there's oxygen or other oxidizing species present, copper and copper alloys are attacked greatly. Nickel can be used under certain conditions. High silicon iron and titanium can be used. Again, titanium depends upon a passive film for its protection, and if we break that down under highly reducing conditions, titanium is unacceptable. Under highly oxidizing conditions in hydrochloric acid, titanium can be used. So we call it a Class 2 material. Class 3 materials are those materials which are generally not used in hydrochloric acid service. And those include carbon steel, zinc, magnesium, aluminum, and lead alloys. Each of these materials typically has corrosion rates that are too great and unacceptable for the hydrochloric acid service. So we would use those Class 1 materials are generally used. Class 2 can be used under some conditions. Class 3 seldom if ever used. And we can use this sort of categorizing system for many of the alloy systems, many of the environments that we look at. Okay, let's shift gears a little bit and talk about sulfuric acid corrosion now. Sulfuric acid is a very important chemical process environment. If we look at the general corrosion rate of steel as a function of hydrochloric acid concentration, we see this strange shaped curve. We see that the corrosion rate starts out reasonably low at very dilute hydrochloric acid, sulfuric acid, and it increases linearly with increasing acid concentration. We get to some level and there's a great decrease, and then the corrosion rate remains at a very low rate for the remainder until we get to very high concentrations. That curve should look somewhat familiar to you if you've seen electrochemical polarization curves. So we see the same shape. Sulfuric acid starts off as mildly oxidizing. When it gets up to a highly oxidizing enough environment, then it's a suitable material for, steel's a suitable material in sulfuric acid. We can look at some specific data for steel and sulfuric acid, and this is what's called an isocorrosion plot. We're looking at the effect of temperature as a function of acid concentration, and what we do is we draw lines across that where we have equal corrosion rates. So if we take a rate of 20 mils per year, it's somewhat like a topographical map. This would simulate 20 mils per year, 50 mils per year, 200 mils per year. What it shows is that sulfuric acid has a reasonably low corrosion rate at several of the acid concentrations for higher acid concentrations. So sulfuric acid can be contained in steel if the acid is highly concentrated. You wouldn't want to rinse it out with water and go to a dilute sulfuric acid. That would attack the steel. Lead is another material that's used in sulfuric acid, and let's look at its isocorrosion. Again, temperature as a function of acid concentration, and we could look at higher magnification here up at the end of the curve, and again we have lines for 5 mils per year, 20 mils per year, 50 mils per year. What you see is that lead is very acceptable for dilute sulfuric acid, steel was acceptable for concentrated sulfuric acid, and so we have a family of curves that can be used, materials that can be used there. There are other materials that are used throughout the entire range of concentration. The isocorrosion plots are a very useful way of looking at those corrosion. Now let's look at the corrosion in nitric acid. Nitric acid is a strongly oxidizing acid. It goes from mildly oxidizing to very strongly oxidizing. And let's look at the effect of chromium in steel on the corrosion resistance in that environment. As we increase the chromium concentration from 4% to 25%, the corrosion rate goes from very high to very low. So clearly chromium, which is favored in chromium in passivating environments, forms of protective oxide, is beneficial for nitric acid. If we look at the isocorrosion curve for stainless steel, temperature as a function of concentration, we see that stainless steel is good over a wide range of nitric acids. So we use the austenitic stainless steels quite often in nitric acid service. We can also generate this plot of class 1, 2, and 3 materials in nitric acid. Class 1 materials are the high silicon alloys. Class 2 materials, titanium and aluminum. Class 3, steel, cast iron, and copper. We would go with the high alloy materials for nitric acid service. The final environment we'd like to talk about here are alkalis. Sodium hydroxide and potassium hydroxide are very strong alkaline environments. We can look at the potential pH diagram for iron and show that iron is quite good under hydroxide conditions except for these very concentrated conditions. If we go to a strong oxidizing, strong hydroxide concentration, then nickel and nickel alloys are the material of choice.
Common corrosive liquid environments include natural waters, fresh, brackish, seawater, geothermal, and brines; treated waters, potable, demineralized boiler feed water, process waters, and cooling waters; and acids and alkalis. Factors affecting corrosion in liquids include physical configuration, chemistry, entrained solids, flow rate, temperature, and biological species present. Microorganisms affecting corrosion include slime-forming bacteria, Desulfovibria or sulfate-reducing bacteria, iron-depositing bacteria, algae, and fungi. Classes 1, 2, and 3 have been established as guidelines to reveal expected behavior of metals in the presence of acid and alkali environments. An isocorrosion plot shows the relationship between acid concentration, temperature, and corrosion rate.
So what we've done is very quickly gone through a wide range of environments and shown their behavior. I would send you to the literature for information on specific environments. What we've tried to do here is go back and relate it to some of the basic concepts we've developed throughout the course. Thank you.